Yeah. So now we will shift a bit from the science that we can do with these laboratories to the gravitational waves to finding more of these new laboratories for doing all the fundamental physics. In particular, I'll be focusing on the survey that is carried out by the Chinese Fast Radio Telescope. And this is a work that I was doing up to last year when I was a postdoc here at the Institute. So just for a context, Max Planck Society and the Chinese Academy of Sciences started a long-term partnership to work on the low-frequency gravitational waves. And this has been discussed already for a while, but I think a plot wouldn't hurt. And basically, this is the range for gravitational waves, and when we refer to low-frequency range, then we are somewhere here. So, for instance, considering pulsars, it will be the range that we can probe with pulsar timing arrays. Now, there are several working packages within this collaboration. The one that we will be focusing is on finding new gravity laboratories and the discovery of 500 plus pulsars. And is this a crazy number considering FAST? Not really, because FAST is a 500-meter aperture radio telescope, which is quite sensitive, the most sensitive we have up to now, especially now that our receiver is no longer available. From FAST itself, we expect to find more than 1,000 pulsars just in the drift scan survey. So up to now, we have something like 3,000 plus pulsars. I think in principle already we reached the 4,000 when we consider the Meerkat service, the FAST, and so many more. So, okay, so we want to find more pulsars, but we already know many. Why do we care about finding many more? I mean, if we want to study pulsars as a population, we already have plenty of them. The idea here is that by finding more pulsars and many more, a fraction of them will be sources suitable to be included in pulsar timing arrays. And also among the thousands is where the exotic one comes. So if we can take a look at since the discovery of pulsars, then with the pulsar service, the number started increasing quickly, and among these 1,000 is when all the milestones came. And for instance, one of them being the discovery of fast radio bursts, which opened up a full new research field. So if we expect to find thousands of pulsars with fast, then a fraction of them will be millisecond pulsars, and from these, a fraction of them will be stable rotators. Because here we constantly say that pulsars are a stable rotator, as stable as atomic clock, but there is a caveat there. Some of them, most of the pulsars, the regular pulsars, they have residuals which are around microseconds. While for the detection of gravitational waves, we want to reach the nanosecond level of tens of nanoseconds. So if we find like thousands of pulsars, that perhaps 5% of them will be millisecond pulsars, and a smaller fraction will be very stable rotators. But also for reaching this point where we have these stable rotators, we find the new source, then we do the monitoring until we have a phase-connected timing solution, and then with the time we start seeing whether this source has the potential to be included or not in pulsar timing arrays. So up to now, I will say, correct me if I'm wrong, that the largest sample of pulsars to be used for pulsar timing arrays is something like 50. So if FAST were to find like a similar number of stable rotators, then it will significantly boost the sensitivity of these experiments. And then coming back to fast sensitivity, here I have placed them to relative scale. So some of you had the pleasure to visit yesterday Effelsberg, which is an impressive piece of engineering. It's a huge radio telescope, and among the largest that you can build that is still fully steerable, which means that it can move. If you cannot go way above that, and instead you need to go to designs such as Arecibo and FAST. So if Arecibo is no longer available, there is a huge gap between FAST and then the next level state-of-the-art radio telescopes. So, considering it anyway, telescopes such as Effelsberg and Parkes are among the largest ones. So we carry on the survey with FAST, which is the commissioning phase started around 2017, but it was done with a not that sensitive instrument, but it was supposed to be like that. It was purely for commissioning purposes, but still it was as sensitive as Arecibo on a good day. And with this already 200 pulsars were discovered, new pulsars. But discovering is the first step, right? We need to time them. And if you consider that FAST expects to find all these thousands of pulsars, but then you need to do the monitoring, then it's more obvious that you will need some other facilities to help you a bit with the timing of these sources. But you cannot move all the sources, right? Because for instance, in some cases, a pulsar for FAST will be super bright in 20 seconds, but for us, we need to integrate for a good hour or so. So anyway, in 2018, FAST was upgraded with its final receiver, 19-beam receiver, which doubled the sensitivity of this instrument. I think it's using this. Yeah. Importantly as well is that during the commissioning phase, FAST was working mostly with a band from 300 to L band. But from this band, most of the pulsars were discovered in the lower part of the band, around 500 megahertz, which is a combination of where the instrument was sensitive, the spectral index of pulsars, and the radio frequency interference around the FAST side. So now going back to this collaboration of FAST with other telescopes, I mean, FAST is also collaborating, or it was as well, with Arecibo, for instance, and GVT, and there are many more telescopes that help to deload FAST. And if you consider the sky visibility of FAST, which is what is shown here, you can see that FAST cannot see below minus 15 degrees in declination and above 65. So in this context, okay, our collaboration FAST Effelsberg parts lies perfectly because the northern sky pulsars can be covered by Effelsberg, while the southern part can be covered by GVT. As I said, there are other telescopes helping as well. And importantly, especially during the commissioning phase, telescopes such as Parkes and Effelsberg were key in bringing FAST up to full speed and the start of the full operations, because when you have an instrument that is that complex, there were some offsets that needed to be taken care of, such as positioning offsets, timing stability, and so on. This is just some results of when we started the collaboration. This is the candidate 1 of FAST that we confirmed with Effelsberg, which we observed 1 hour, FAST detected it in less than 50 seconds. And although our search parameter space is reduced because we have some prior, we have the DM, we have the spin period, still we need to carry on with some of our more advanced algorithms, such as template bank or acceleration searches and fast folding algorithms. Because, for instance, for a binary system, FAST might not detect acceleration in 50 seconds, but we, with 1 or 2 hours, we do. So we need to account for this, otherwise we're not able to recover the pulsar. And the collaboration has led to several papers. We are definitely behind the pulsars that we need to report now. Most of the ones that are shown here come from the early part of the FAST survey, so many more papers to come. And just as a highlight, perhaps this is the best plot that summarizes everything, so the spin period derivative, where you see the different populations of pulsars. So the one in black are the ones that Effelsberg has been monitoring and for which we already presented the timing solution, so it's already published. And in red is the one that we're monitored by FAST. So you see that from these 25 pulsars, already 12 of them are millisecond pulsars. Although 11 of them are with binary companions, but mostly white dwarfs. So perhaps there is some potential there if we continue studying them for them to be stable rotators. And for the Effelsberg part, I will go very briefly. I'm highlighting here the black ones are the ones that we already reported, and the one in magenta is the one that we are working on now. So most of the pulsars that we observe at least are classical pulsars. Many of them are quite old and located close or below the depth line, although you might argue that where is really the depth line, so the point where we no longer detect pulsars. Some of them are millisecond pulsars. This one is isolated, and this is a manually recycled pulsar, so not fully a pulse. The accretion process didn't go effective enough for it to be spin up to spin periods of milliseconds. And I will jump this highlight, but this is the same pulsar here. So this manually recycled pulsar, it's at a 95 days binary period. And its companion, it's a massive one, a carbon-oxygen white dwarf, and if you compare similar systems, this is the one that seems to be in the widest orbit. We continue monitoring this source because in addition to this, it's also one of the sources that tends to disappear, and we are still not clear whether it's intermittency or scintillation. And the natural question to ask is like, okay, all these pulsars that we have discovered with FAST, I mean, like the project promised 500, we are more or less like a 300, but this is just the drift scan survey. There is another survey, which is the galactic plane survey, that also has like above 200 pulsars. But for the ones that we were monitoring, the natural question is to say, well, could we have detected these pulsars before, like other telescopes? And then when we compare this, and this is what is plotted here, so what is shown here, the different surveys, like for instance the one with Arecibo with GVT at lower frequencies, because FAST was observing back then at lower frequencies, we concluded that most of these telescopes would have been able to detect these pulsars. Now, because some of them they observed for something like 60 seconds, perhaps you could say, okay, they were low DM, so scintillation, and that's the reason why we didn't detect them. We haven't, in principle, searched the data of this telescope to say, indeed, the sources are there or not, but it's important to notice this, that these sources were observable. Now, with the sources that we have discovered now with FAST, with the 19 beam receiver, yeah, most probably no other telescope would have been able to detect it because of this huge gap in sensitivity. So having said that, I will, instead of a summary, I will just like to finish this with some reflection on what to do with the bottleneck that is coming to appearing, which is all the detections that we expect from the most sensitive state-of-the-art radio facilities. So FAST, MIRCAT, SK, and so on. Each of them expects to find thousands of pulsars. But finding the pulsar, it's the first step. It's a milestone, but it's the first step. We need to monitor them. So for each of them, we need regular monitoring and observations to obtain the timing solution that allow us to do science. Then how do we manage this? One option could be, yes, you upgrade the next generation instruments. For instance, like Eversberg, it's been constantly upgraded with EDD, which boosts the signal to noise, and now with UVB as well. Or we could also build low-cost but dedicated instruments, something like Chime, just to do the monitoring, and if you want to spend 24 hours on source, you can do so. Anyway, this problem of monitoring all the sources needs to be addressed somehow. So thank you very much for your time.
Thank you, Marilyn. Questions? I have.
I know that they want to go wider in the frequency range because now it's quite narrow, right, from 1 to 1.5 gigahertz. But I haven't heard that whether they're already installing something or building it. But most probably, yes, I think they were working with Parks for a wideband receiver, yes. I'm not sure, yes. Of that, I do not have the numbers, but so MIRCAT is also doing an all-sky survey, right? But MIRCAT, the equivalent telescope size is something like Eversberg as well, or?
Full array gain is 2.8.
Yeah, 2.8. Okay, yeah, for Eversberg is 1.4, something like that, so it's double more sensitive. So no, I will expect still fast, expect to find many more, yeah. But MIRCAT has already like, how many new pulsars?
More than 200.
More than
but
200.
Most of those are in pointed surveys.
Okay.
Where we have an advantage outside for all sky surveys. Of course, MIRCAT has the disadvantage that we have to produce many beams because of the interferometer.
Yeah.
It's an advantage that single dishes will also always have that you cover more area in the sky per beam.
Yeah. So yeah, for FAST itself, when you here I was presenting these 200 plus pulsars, but it's from the drift scan survey, so you leave your feed and then the sky just moves. But the other survey, the galactic plane survey, I think it has even found many more pulsars than this one, something like 300 already.
Usually, the pulsar surveys done by MIRCAT does not overlap with the part where FAST can survey. But some sources can be followed, but I'm not sure if we follow them.
But I think Mercury is already quite busy itself with its own pulsars. Okay.
Just an additional comment on what Vishnu said, we actually designed the galactic survey to look at so that we don't see this strange fastness.
Okay, yeah, in terms of also sky location, FAST is not really privileged with the galactic center. So.
Yes, any other questions? No, we are actually out of time, so thank you, Marilyn.